Math 1314, Tyler Junior College, section 3.4, zeros of polynomial functions. Rebuilding functions, the linear factorization theorem. This is kind of a big theorem, but at the same time, it's also crazy intuitive if you followed what we've done so far. The linear factorization theorem basically says the following. If the zeros of a polynomial function, and I've only listed the leading term, a sub n times x to the n, plus more stuff at the end. I'm assuming this is a degree. If the zeros of a linear function are c1, c2, all the way through cn, so we've already found the zeros. Here they are, all of them. Now some of them might be repeated, but that's okay. Then we can write the function a different way. The factor theorem says every zero has a factor associated with it. So if c1 is a zero, then the factor associated with it is x minus c1. And if c2 is a zero, then the factor associated with it is x minus c2. All the way down to x minus cn. But that's not sufficient. Because if we were to multiply all these out, to get the leading term, we would have to multiply all the leading terms of the factors. And there are n factors, each of which leading term is x. So multiplying x n times in a row would give us x to the n, but not the necessary leading coefficient. So we put the leading coefficient in front. Now, why do I call this rebuilding functions? Because I can build a function that has the zeros I want. This is how I made some of the problems in previous videos happen. I started at the end with the zeros I wanted, built the factors, and remultiplied. But again, this really shouldn't be a surprise, because at the beginning of this series, when we talked about the rational zero theorem, we reversed the process by putting zeros back into factors and remultiplying. So this is just kind of summarizing something that we've already seen. But how can this be posed as a question? Let's say that, suppose x equals 4 and x equals 3 plus 4i are zeros of f of x, and f of 1 is equal to, I have no idea how this is going to work out, we'll say 10. Find f of x, assuming a minimal degree. Now, what do I mean by that? Well, our function has to have some degree. We want to find the one with the smallest possible degree that does this. Now, do you know what the degree of this has to be? Well, according to the corollary to the fundamental theorem of algebra, the degree matches the number of zeros if you include multiplicities. How many zeros do you see? 2. But this zero is not real. Complex, non-real zeros occur in conjugate pairs. So even though I'm only given 2 zeros, there's a third one implied. Since zeros occur, non-real zeros occur in conjugate pairs, comma, x equals 3 minus 4i must also be a 0. So I have 2 zeros given and a third implied 0. So I have to have a minimum of 3 zeros, aka a minimum of 3 factors, aka a minimum of a third degree polynomial. This minimal just prevents me from tacking on more factors unnecessarily. So now that I have all 3 zeros that must be zeros, I can build my function. So my function has to be of the form an, we don't know the leading coefficient yet, times x minus each 0. X minus 4 is easy. But how do we do the other ones? Answer very carefully. The next factor is x minus parentheses 3 plus 4i. x minus this 0. And the third factor is x minus this 0. So x minus parentheses 3 minus 4i. Now I will admit that what's about to happen is much easier if our zeros are all real and integer or rational. But whenever they're irrational or non-real, it gets a little ugly, but manageable. So we need to follow all this out because technically we have our function, except we don't know the leading coefficient. When I say find the function, I mean find the polynomial in general form. Something x, well we know it's a third degree polynomial, something x cubed plus something x squared plus something x plus something. So how are we going to find all that? Well, we need to bust all this open, do a lot of multiplying. Believe it or not, you should start with these two guys, as ugly as they may seem. I'm going to drag down everything that's not doing anything so I don't forget about it. The first thing we need to do within each factor is get rid of the unnecessary inner parentheses by distributing the negative across it. So this middle factor will be x minus 3 minus 4i, and this last factor will be x minus 3 plus 4i. Again, that's from distributing the negative across each of these smaller parentheses. And now I got a whole heap of multiplying to do here. Now, you can multiply these by just distributing 3 times over. Distribute the x across here, distribute the negative 3 across here, distribute carefully the negative 4i across here. Gather like terms, clean up all your i's, and pray for the best. Now that being said, I'm going to show you a gimmick for multiplying a trinomial times a trinomial. Actually, this gimmick will work for any two polynomials, even as small as a FOIL problem. But one gimmick for multiplying polynomials is to set up a table that has the same number of rows and columns as there are terms. Each of these has 3 terms, x negative 3 negative 4i, x negative 3 positive 4i. Since each has 3 terms, I'm going to set up a 3 by 3 table. Across the top, I'm going to write the terms of one factor. We'll use x minus 3 and minus 4i. And across the left, I'll write the terms of the other factors, x minus 3 and positive 4i. To multiply all of these, all we have to do is fill in each box with the product of what's on top and what's on the left. For example, this box will be x times x, which is just x squared. That was easy. This box is negative 3 times x, which is negative 3x. That was also easy. This one looks funny. Negative 4i times x is negative 4ix. Looks weird, but it's the correct product. Continuing. This box is negative 3 times x, which is negative 3x. This box is negative 3 times negative 3, which is positive 9. This box is negative 3 times negative 4i, which is positive 12i. And then the last one, you need to be really careful, especially at the end. This box is positive 4i times x, which is positive 4ix. This box is positive 4i times negative 3, which is negative 12i. And then the last box is positive 4i times negative 4i, which is negative 16i squared. Hey, we haven't seen that in a while. Do you remember what to do with an I squared? I squared equals negative 1. This is negative 16 times negative 1, so we can just change that to positive 16. And now we just have to gather like terms. Before we do that, let's go ahead and bring down everything that's not changing. an, and the x minus 4 is still the same, but we're about to multiply these together. And if you're thinking, I didn't leave enough room, trust me, I did. Let's find our x squareds. That's the only one. Let's find our x terms. Here's 1, here's 1, and these are also x terms, but do you notice something? They cancel. Those are the only x terms. So negative 3x and negative 3x is negative 6x. Let's gather up the constant terms, the things without x's. Oh look, here's another pair of opposites. When you set up these factors based on non-real conjugates, all the i's drop out. Either they get squared or there's somebody to match them to cancel. So that leaves me positive 9, positive 16, which is positive 25. Oh, I'm not out of the woods yet, now I gotta multiply these guys. And again, you can just distribute x times all this, negative 4 times all this, or you can set up a table. I think I'll set up another table. This gimmick for multiplying polynomials is really overlooked. It's handy because it helps keep things organized. I'll need a 2x3 table because it's 2 terms sums 3 terms. So we'll do it like this. The binomial is x minus 4, so I'll put x minus 4 here. The trinomial is x squared minus 6x plus 25, and now I just have to fill in each box with its product. X times x is x cubed. Excuse me, x times x squared is x cubed. X squared times negative 4 is negative 4x squared. Negative 6x times x is negative 6x squared. Negative 6x times negative 4 is positive 24x. Watch your signs. Positive 25 times x is positive 25x. And then positive 25 times negative 4 is negative 100. So let's gather up all the like terms. There's only one x cubed. We have negative 4x squared and negative 6x squared, which is negative 10x squared. We have positive 24x and positive 25x, which is positive 49x. And then lastly, we have minus 100. So we almost have everything we need. The only thing we don't have is the leading coefficient. So how are we going to find that? Well, there's one piece of information we haven't used. In upper level math classes, it's called an initial condition, a condition that's given to you initially at the beginning of the problem. The only thing we haven't used yet is the fact that when I put in 1, I get out 10. F of 1 is equal to 10. So how can I take advantage of that? Well, I know that when I put in 1, I can put it here. So I get some unknown leading coefficient times 1 cubed minus 10 times 1 squared plus 49 times 1 minus 100. But I also know that this is supposed to equal 10. So I have 10 equals all this mess. Now speaking of all this mess, let's start cleaning up this parentheses. 1 cubed is 1, 10 times 1 squared is 10, 49 times 1 is 49 minus 100. And now the contents of the parentheses are just a number. Let's figure it out real quick. 1 and 49 is 50. 50 minus 10 is 40. 40 minus 100 is negative 60. Well, shoot, I just have to divide both sides by negative 60. And so my leading coefficient is 10 over negative 60, which reduces to negative 1/6. Therefore, my function, and it's okay to leave the negative 1/6 factored out, is negative 1/6 times x to the third minus 10x to the second plus 49x minus 100. Or, if you wanted to distribute the negative 1/6, negative 1/6 x to the third plus 10/6, which reduces to plus 5/3 x to the second, minus 49/6 x plus 106, which reduces to 50/3. So both are acceptable. The second one is just completely in general form because it has no parentheses. So rebuilding a function is actually pretty straightforward. Every zero becomes a factor. Factors get all multiplied out. And with an initial condition, you can recover the leading coefficient. If you don't have an initial condition, you can assume the leading coefficient is whatever you want. If I can assume it's anything, I would assume it's 1. And remember that complex non-real zeros occur in conjugate pairs. So it's a task to do, but conceptually, it's a pretty straightforward setup. And that concludes this series of videos for section 3.4, zeros of polynomial functions.